Here we have an example where we're finding the hydronium ion concentration of a weak acid solution. And of course this is the first step in finding the pH. We can't calculate the pH until we know the hydronium ion concentration. Before a weak acid solution, we need to set up an equilibrium expression and an ice table in order to calculate the hydronium ion concentration. So here's our problem. Find the hydronium ion concentration of a 0.1 molar HCN solution. So this is hydrogen cyanide, which can act as a weak acid. So our first step is to write the balanced equation for the ionization of the acid and use it as a guide to prepare an ice table, showing the concentrations of the weak acid as the initial concentration. So we don't need to calculate Q here because we have the initial concentration as 0.1 molar HCN, and therefore the only way this reaction can go is to the right because that's our initial concentration. Here we have HCN plus water yields H3O plus cyanide. Okay, that's our balanced equation. So if this is acting as an acid, then water must therefore be acting as a base. The conjugate acid of water is H3O plus, and the conjugate base of HCN is the cyanide ion. So we have our initial conditions here, 0.1 molar HCN, and initially we have essentially no hydronium and no cyanide ion. We don't count the autoionization of water here because it's negligible compared to the 0.1 molar HCN solution that we're adding to the system. Step 2 is to represent the change in concentration of hydronium with the variable X. And so we want to define the changes in concentration of the other reactants and products if applicable in terms of X. So in this case we're losing X of our HCN and we're gaining X of the hydronium and gaining X of the cyanide. Why is that? Because for our balanced equation we have a 1 to 1 to 1 mole ratio. So for every 1 mole of X of HCN that we lose, which we're calling X, we'll gain 1 mole of H3O plus and 1 mole of the cyanide. So we're saying we don't know exactly how many moles that's going to be, so we're just going to call that X. That was our change in concentration, and now we need to write the equilibrium expression for each of these. And so if we lose X amount of the HCN, then at equilibrium we're going to have our initial concentration, which was the 0.100 molar, minus that X that we lost for our starting material. And for our products we will have gained X of the H3O plus, so we have X of that, and for the cyanide we have X of that. Now this is what we call an ice table. So I want to go back and explain what that means. That stands for initial, change, and equilibrium. So initially we write down what we have at the beginning. Then we write down how that changes as the reaction reaches equilibrium. And then what we have, the amounts that we have at equilibrium. And if we aren't given numbers that we can work with to plug those amounts in, then we have to express that in terms of X. And knowing the K for the acid will allow us to calculate that X and go back and plug in for that and find what we would have at equilibrium. So in this case, once we find X, we'll know our hydronium ion concentration at equilibrium, and therefore we can solve for the pH. So next we take the equilibrium row, this row that we have right here, and we bring that forward into a K expression. So remember from the last chapter, K is equal to our products over reactants raised to their respective coefficients. And in this case, the coefficients for all of these is 1. And for most of the acid problems, that will be the case. We call this the Ka because it's the K for our acid. So what we have here is our equilibrium row put into our K expression as products over reactants. The products of this reaction were H3O plus and cyanide, and the reactant was hydrogen cyanide, which is a weak acid. Now, we're going to plug in what those values were from our equilibrium row, or what those variables were, and that gave us X times X, because the H3O plus was X, the cyanide was X, and the HCN was what? It was 0.100 minus X, right? And so that gives us X squared over 0.100 minus X. So if we work this equation out and we distribute, we set this equal to the Ka for the acid, which is 4.9 times 10 to minus 10, and we distribute everything across, then we're going to have a quadratic equation, which is going to require us to plug that into the quadratic formula to find the answer. But we have a little shortcut we can take in many of these weak acid problems, and that is to assume X is small. If we assume that X is small, then the amount of X that we are losing from our initial acid amount that we put in, which was 0.100 molar, a 0.100 molar concentration, we assume that it isn't going to ionize very much. And notice that the Ka here is 10 to minus 10. And so with a Ka that small, then the X that would be lost from 0.1 molar is very, very small. And therefore it wouldn't be enough to add a significant amount or change our significant figures by an amount that would make a difference. We wouldn't notice a difference in our significant figures, and therefore we can make the assumption that X is small, and we can take this shortcut, meaning that we can not consider the amount of X that is subtracted from the initial amount, and therefore we just eliminate it because X is small, and it makes our calculation much easier. We don't have to plug in the quadratic formula. And so now we can solve for X a little bit easier. Okay, and the way we can do that is we can take the square root of both sides and solve for X, and we get X is equal to 7 times 10 to minus 6. Okay, and so that is our H3O plus concentration. Now that's all that we were required to find here, was the H3O plus concentration, but you can just go ahead and calculate the pH. If you take the negative log of that, you can calculate the pH from this value. If the amount that we subtract is larger than 5% of the value that we're subtracting it from, then our X is small approximation is invalid. And so here's the way we check that. We take our X that we just calculated and we plug it in to a formula which is saying that how do we calculate percent? Percent is part over whole times 100. And so we're going to plug in the amount that we're subtracting for X, which was 7.0 times 10 to minus 6, divided by the initial amount, which was 0.100, and times 100, and what we got was 7.0 times 10 to minus 3. And that is much less than 5%. If that amount is greater than 5%, then we have to assume that our X is small approximation is invalid, and we have to go back and solve this with the quadratic formula, because we can't take the shortcut and assume that X is small, because it's much larger than 5%. It has to be less than 5% in order for this to be valid. In this case, it is less than 5%, because 7 times 10 to minus 3rd is less than 5%, and therefore our approximation was valid. We can even check our answer further by plugging our numbers that we got back into our original K expression and see if it matches the K that we used to calculate our x. And so we can just plug it back in here. So we got 7.0 times 10 to minus 6 for x, and if we square that and divide by 0.1, we get 4.9 times 10 to the minus 10. And if we go back up, we see that's exactly what we found for, or what we used for our k value, and therefore the Ka matches the original Ka value, and that's another reason why our answer is valid.